Hello, my name is Shervin Naeli, and today I'm going to be going over substitution, which is the first technique of integration taught to introductory level calculus students. It involves using the variable u to substitute a polynomial in the integrand. Before I get into the video as a whole, I would like to recommend 3 Blue 1 Brown's Essence of Calculus series, and specifically his video about integration, Chapter 8. His series is fantastic and practically mandatory viewing for any introductory level calculus student. His explanations of concepts are intuitive, engaging, and all around incredibly helpful. Now for a quick review. So, integrating the first derivative of a function will return the original function, as displayed mathematically here. The integral of f prime with respect to x is equal to f of x plus the constant of integration c. The integral of a function will return the primitive function. The integral of f of x with respect to x is equal to big F of x plus c, the primitive function being the function that was differentiated in order to get the function at the beginning. Now this is the formula for substitution. The integral of f composed of g of x times g prime of x with respect to x is equal to the integral of f composed of u with respect to u, which itself will become f of u plus c, which we can then sub back in g of x for u, giving us the final function big F of g of x plus c. What this basically does is it reverses chain rule. We use u to substitute out a polynomial in order to reverse a chain rule derivative. Okay, so now without any prior knowledge other than the fact that u is usually used to sub out a polynomial, let's just give a crack at this problem, Let's see what we can learn by just going all gung-ho and trying it out for ourselves. So, the first thing I notice about the integral of 3x squared times sine x to the 3 with respect to x is that x to the 3 and 3x squared are actually related, because 3x squared is a derivative of x to the 3. This should probably stick out to anyone who's done differential calculus. So how about we just set u is equal to x to the 3, right? So that the derivative of x to the 3, or du over dx, is equal to 3x to the 2. Now, let's just sub in those for 3x to the 2 and x to the 3. So we have du over dx sine u dx, as the thing we're integrating. And oh wait, let's just cross out the dx's, because that looks like a fraction, and that's in the numerator, so we can just cross them out. And now we have sine of u du, forgetting the fact that we're now integrating with respect to u and not x, and the x just kind of disappeared. Then if we just integrate sine of u with respect to u, we get negative cosine u plus c. And remember, u is equal to x to the 3, so the answer is negative cosine x to the 3 plus c. This has to be wrong, right? We treated the derivative operator, the derivative function, as a fraction. That's like a math sin right there. Okay, well, one of the nice things about integrals, or indefinite integrals, is we can just get the derivatives of them and check to see if they're the same as the original thing that we integrated, and that way we can check to see if we were right. So we have our function negative cosine x to the 3 plus c. We get the derivative of that. That becomes sine of x to the 3 times 3x squared. Oh, so we were right. What the hell is going on here then? Because what we did seemed obviously wrong. We seem to have jumped like 50 hurdles to get to the answer we did. And the answer is differentials. Remember dy over dx? What does that mean? Well, it's a tiny change in y over a tiny change in x. Okay, now I would like to go over the function y is equal to x cubed. And I want to quickly zoom in so I can show something better a little bit later. We know that dy over dx is equal to 3x squared. The derivative of y with respect to x is equal to 3x squared. Well, how about I represent dy and dx visually? Of course, this isn't 100% accurate, because after all, dy and dx are supposed to approach 0. However, I want to give you a chance to really realize what's going on. Dy dx is the ratio between the tiny distance dy over the tiny distance dx. So it would make sense if we could multiply dx by 3x squared to get dy. Visually, that makes sense as well. You can multiply dx by something, in this case it would be 3, to get dy. Again, that's because I've zoomed around. Again, that's because I've zoomed in at the x equals 1 point. It would also make sense that dy over 3x squared is equal to dx, since we can treat them as independent quantities. The final key to solving this problem is to realize that the dx in the differential statement is the same as the dx in the integral statement. They both mean a tiny nudge to x. Now, before we do anything else, I just want to make it clear that what we did before was a notational disaster. All right? Now let's attempt to solve the same integral as before, this time with an attempt at being notationally consistent and accurate. Again, we are going to use u in place of a polynomial to make our solving process a little bit simpler. We have the integral, 3x squared times sine of x to the 3 dx. Again, let's set x to the 3 is equal to u. So du over dx is going to be 3x squared. We're not going to do anything with that just yet, but let's sub in u for x to the 3. Now I would like to solve for the differential du, which we can get by multiplying 3x squared by dx. Now look back at our integral. We can rearrange what's in the integrand to get 3x squared dx, and thus we can substitute that out for du. So here I've done that, sine of u times 3x squared dx, and since we know these two are the same, we can now just make it sine of u du, which means that we are now integrating with respect to u and not x. Okay? From there, it becomes a breeze to solve. The integral of sine of u is just negative cosine u plus c, and then once we're done, we can sub back in x to the 3 for u, and that would be our final answer. You may be wondering, what do I pick to be u? What part of the integrand do I select to be substituted out for u? And you need to remember that u is a polynomial. So you should either watch out for a reverse chain rule, that is, look to see where a chain rule occurred and see where you can reverse that with a u, or if you can't find any, sub u in for a polynomial raised to a power. Now for something a little bit more challenging. The definite integral from 0 to 10 of x over x squared plus 2 dx. You may notice that there is no obvious chain rule going on, so we can't just move things around and say, oh, this equals du and solve like that. However, you will notice that in the numerator, x is raised to the power of 1, while in the denominator, x is raised to the power of 2. What this means is that the numerator is just a constant away from becoming the derivative of the denominator. This is useful for us, because that means that we can later cancel it out. You'll see what I mean as we go on. So let's set u is equal to x squared plus 2, and then rewrite our integrand to be x over u. Now let's solve for the derivative of u with respect to x, which is 2x. bear in mind we're looking for the differential, du, which is 2x times dx. This time, however, I want to do something else. Instead of solving for du, let's solve for the differential dx, which is du over 2x. So now, instead of dx, we write x over u times du over 2x. Okay, but something else has happened here, right? The bounds of integration have changed from 100 to 102. What the hell just happened? Well, this was actually implicit in the original statement, but those original bounds of integration are x is equal to 10 and x is equal to 0. Considering that we're now integrating with respect to u, it's important that we rewrite those bounds to be in terms of u. Don't worry, they're still pretty much the exact same. It's just we're writing them in terms of u. If you'd like to completely simplify the integral out and then plug back in x, you can also use the original bounds in that way. We're just going to write the bounds in terms of u and solve with the bounds in terms of u. So this simplifies out to be 1 over 2u du, to which I will take out the 1 over 2 of the expression, to which we just have the integral of 1 over u with respect to du. I would like you to recall that the integral of 1 over x with respect to x is equal to ln of x. I would also like you to recall the fundamental theorem of calculus, that the definite integral of f of x from the bounds a to b is equal to its antiderivative evaluated from a to b. So then, our integral would be equal to 1/2 ln 102 minus ln 2. Or in other terms, around 1.9659. Finally, I want to do one more indefinite integral. The square root of 1 minus the square root of x. A nested square root, all with respect to x. So let's set u is equal to 1 minus the square root of x, such that our integral becomes the square root of u dx. Now let's differentiate both sides, and what we'll get is that du over dx is equal to 1 over negative 2 square root of x. Now we can find the differential du, which is equal to negative 1 over 2 square root x times dx, and then isolate to get dx, which would be negative du 2 square root of x. So let's plug that in, right? The square root of u times negative du 2 square root of x. And now we can rearrange and bring the constants out of the integrand. So now we have the square root of u times the square root of x. What do we do here? Well, we already have an expression that solves for u in terms of x, right? U is equal to 1 minus square root of x. So what if we use that and we change our x term to be in terms of u? So we know that u is equal to 1 minus square root of x, so the square root of x must be equal to 1 minus u. Thus, we can rewrite our expression to be negative 2 times the integral of square root of u times 1 minus u du. That becomes negative 2 times the integral of the square root of u minus u to the power of 3 over 2 with respect to u. This, if you remember, splits into negative 2 times the integral of the square root of u with respect to u plus 2 times the integral of u to the power of 3 over 2 with respect to u. From there, it's a simple power rule antiderivative. Thank you so much for watching.